All right, so I came up with a few practice problems for us to try. I think most of these are from the homework or close to the homework. So let's say we have a plot of natural log of the rate versus 1 over t. So this is an Arrhenius plot. And we're given an equation for the line that is shown here. And we want to calculate the activation energy. Okay. So we know that this equation, y equals mx plus b, for that line, in terms of the Arrhenius, is essentially ln of k equals minus EA over R times x, which is 1 over t, plus natural log of A. So that's the Arrhenius equation. That is what we're fitting when we plot ln of k versus 1 over t. This is that equation for the line in terms of the variables that we need in the Arrhenius. So if we're given the slope and we want to calculate activation energy, what do we need to do? So the slope minus 16,108 is equal to minus EA over R. And which R do we use? Remember? What's that? Yeah, so we're going to multiply by both sides by negative R. Okay, which R? 8.314. So this is joules per mole Kelvin. Okay. So that's going to be multiplied by minus 16108. And that should give us, our activation energy. Back to my notes. And we're going to end up with 134 kilojoules per mole. So watch when you're doing your Arrhenius equation, watch what the units on R are. Joules per mole Kelvin. Usually we give activation energies in kilojoules just because they're usually very large numbers, so keep an eye on those. Okay. Everyone okay with understanding what the slope is, the EA over R? Yes. No, so we multiply, I just left it off. We might multiply both sides by minus R. Yeah, and then that negative will go away. Yes.
It's negative activation energy in this case because the slope is negative.
The slope is negative. We will always see a negative slope for this type of plot. The activation energy is going to be positive because our slope is going to be equal to minus EA over R, and our slope, the value of our slope, is going to be negative. So that negative is going to cancel. Yes?
How do you know which R to use?
Yeah, so usually the clues are in the units, although I would say with this Arrhenius equation is not super obvious. When we do, so when we're doing Arrhenius, always use 8.314. When we are doing the and KP, so I have one of these. Let's go there for now. I think I have one. Slide 2. I like this one. There's a multi-step And then we're going to draw a energy profile diagram or reaction coordinate diagram, however we want to call it. We're going to look at this two-step reaction. We're going to first write the chemical equation for the overall process, identify intermediates, identify catalysts, predict the rate law if the first step is rate determining. Do we know what rate determining means? It means it's the slow step. Okay, it's also written up there. And then draw our energy profile diagram. So I'll let you all work on that. Okay. Hopefully that was at least enough time to get started. So writing the chemical equation for the overall process. It's nice to do this first, even if the question didn't pose that first, because that helps you identify what the intermediates are and if there are catalysts, which is in part B. So if we look at our two reactions, we have I minus that shows up on the reactant side in the first step, and I minus that shows up in the product side of the second step. And we also have IO in the product of the first step and then in the reactant of the second step. Okay. Those are all going to cancel. And then when we add up the remaining reactants of products, we're going to have 2 H2O2 forming 2 H2O plus O2. And if you want to check your work, you can always make sure that you have the same number of hydrogen and oxygen on both sides of the arrow. Okay? So that's going to be our chemical equation for the overall process. What intermediates or intermediate do we have? IO, yes. So IO minus is going to be the intermediate. It's produced in the first step and used in the second step. Okay? What about catalyst? Yeah, I minus. So I minus is our catalyst. We know it's a catalyst because it's a reactant in the first step and it shows up in a product in the last step. Okay, so it wasn't consumed in the reaction per se. It was used, but it wasn't consumed. Okay. Does that make sense? Okay. All right, so if we assume that we have a slow first step, we can write our rate law fairly easily. Rate equals K times the concentration of H2O2 times the concentration of I minus So we're assuming that, well, because it's an reaction mechanism, we know this is an elementary step. And because of that, we can write the rate law from the reactants. And since the first step is slow, all we need to worry about are the reactants in the first step. Yeah.
So I know it matters with equilibrium, but for finding rate laws, does it matter if it's aqueous, solid, liquid, gas?
Okay, so the question is, does it matter if what the phase is for these things when we're writing the rate law? And actually, no, it doesn't. So they're going to be included if they're reactants. Yeah. And the other thing is that we said that I minus is a catalyst. Catalysts can be included in rate laws. Intermediates cannot be included in rate laws. So if you have an intermediate in a rate law, you probably don't have the right rate law. Okay, then drawing the energy profile diagram. Maybe the most important part of this question. That almost says energy. Okay, energy versus progress. It says to assume that the reaction is exothermic. All right, so what does that mean for the relative energy of reactants and products? Yeah.
That means that the products can have a lower energy than the reactants?
Yes, excellent. Products have a lower energy than the reactants. So we're just going to write products and reactants. Okay, that's good enough for this drawing. And we know we have an intermediate, and we know we have a two-step reaction mechanism. So we have one intermediate, which is going to have lower energy than the activation energy, so it goes downhill. And we're going to have two hills because we have this two-step mechanism. Now, I don't know if this is completely accurate for this reaction, but if you drew something along these lines, okay, that's good. If we had more information, we could tell the relative heights of these activation energies. Okay. But given what we have, we'll do that. Yes. Oh, yes, that's right. Actually, we do have the information. Yeah, so yeah, you said that the first activation energy has to be higher, and that's correct because we know that our first step is slow. So the first activation has to be higher than the second activation energy because that higher activation energy means a slower rate. Slower rate, that's our slow step. Okay? Thank you. Totally forgot about that. Does that make sense? Cool. All right, so we have some more. Predict a rate law with the fast first step. Yeah, so Kc, and we're going to convert between Kc and Kp. So Kp equals Kc times R times T times to the raised to the delta N. So here, this R is the other one, 0.0821 liters times atmospheres over moles times Kelvin. And when we're thinking like how to sort of justify this one, when we're working with equilibrium, we're always working with concentrations, so moles per liter. And if we're multiplying by R in liters per moles, that's going to cancel those out. So we're sort of following the units there on that. Does that help a little? Okay. Other questions? You don't want to try this one? Okay. I'll let you work on it for a few minutes. Notice that we have Kc's in our two equations here. All right. How do y'all feel about this problem? Good. Okay. How many of you solved for or converted the KCs in the two steps to KPs first? A couple of you. And how many solved KC and then at the end did KP? Yeah. Either way is fine. Just was curious. Okay. So I waited till the end to do KP because I don't like using that equation for some reason. I don't know why. It's pretty straightforward. I just don't like it. In order to add up to this equation, the first thing I did was reverse equation 2. Okay, so that's the second one here with the large Kc value, which gives me then N2 plus O2 in equilibrium with 2 NO. And when we reverse a reaction, we do 1 over the K value. So we do 1 over 2.1 times 10 to the 30. Okay. And then I'm going to add to that equation 1. So because now we've got our NO, which we're going to cancel out on both sides of the equation. We have our NOBR on our product side if we simply add that first equation, and then N2 and O2 on the reactant side because we reversed the second one. So we'll do 2NO plus Br2 in equilibrium with 2NOBr. We don't have to do anything to that R, or excuse me, to that K. Add them up. The NOs are going to cancel. We'll get N2 plus O2 plus Br2 in equilibrium with 2 NOBr. And we now, when we add equations, we're going to multiply the K's together. So 1 over 2.1 times 10 to the 30 is 4.8 times 10 to the minus 31. And multiply that by 2. And we'll get 9.5 times 10 to the minus 31, and that is Kc. We agree? Okay, cool. And then to solve for Kp, Kp equals Kc times R times T in parentheses to the delta N. Delta N is a simple mathematical calculation. Make sure you're only looking at the gases when you're using delta N. Okay, that's an easy place to make a mistake. And we're looking at the overall equation here for converting. We're looking at this equation for converting or to get our delta N. So we have 2 moles of products. This is our stoichiometric coefficient of 2. So delta N is going to be the moles of product minus the moles of reactant. So we'll have 2 minus 3. There's a total of 3 moles of reactant, so we have minus 1. And I think I messed up on my calculation in my notes. So I'll have you all tell me what the answer is. 9.5 times 10 to the minus 31 times R, 0.0821, times T, which was 298, to the minus 1. Maybe I didn't do it right. I don't know. What did we get? .89 times 10 to the minus 32. Okay. Cool. That is actually what I got. I did it right. All right, cool. Questions on that? Yes?
Do you think we'll ever have to on the test tomorrow balance the equation or no? To get the right delta N?
That's probably not what we're going to test you on. It's kind of not like the goals this semester. So it doesn't hurt to check. Other things. Okay. Let's do conjugate acid base pairs. Okay, so we are going to, in the first part, write the conjugate base of those Bronsted-Lowry acids. In the second part, write the conjugate acids. I'll let you all work on that. All right, I'm gonna work these out here. So I wrote the definitions for Bronsted-Lowry acids and bases. So Bronsted-Lowry acid donates a proton, a base accepts a proton. Okay. Because we're asked to write the conjugate base of these two acids, all right, we know that a proton has to go away. All right, so these are acids. They are going to donate some protons. These probably should be equilibrium arrows. You don't need to know exactly which one of these protons to have disappear, but one of them needs to go away. Okay, so the Bronsted-Lowry, the conjugate base, is HCOO minus. So whenever you take away a proton, you need to increase the negative charge on the species. Okay? So we went from a neutral acid to a conjugate base with a -1 charge, and that +1 is over here with our H+. Yes?
Would it also have been acceptable if you wrote COOH minus?
Yes.
Okay.
Yeah. We're not going to worry about that stuff. Yeah. Okay. Everybody okay with that? So watch your charges, which with HPO4 2-, again, this is what we call amphiprotic, so it can act as either an acid or a base. In this problem, we're saying it's an acid, which means it's going to donate its proton. Whoop. And so we're going to form PO4 3-, and then that H plus in solution. So our conjugate base is the PO4 3 minus. So again, we went from a 2 minus on the acid to a 3 minus on the base.
So with the conjugate bases, is it like safe to kind of just get rid of the hydrogen if it has one?
Yeah, so if we're dealing with the definition of Brumsted-Lowry, or Lewis really, and we want to form, we go from an acid to a base, just get rid of that, get rid of one proton. Okay? Don't forget to affect the charge, change the charge. That make sense for everyone? So then on the next part, now we have bases, we're going to write the acids. In order to actually balance these out, we have to add water. If we want to write equations, we could just write the conjugate, but this makes me feel better when I do this. The proton has to come from somewhere, so it's going to come from water. When we write out the conjugate base of SO4 2 minus, we have HSO4 minus, and also OH minus is formed from the water. Okay. So again, look at our charge. We went from a 2 minus as our base. We add a proton, so we increase that. The charge goes up +1. Okay. Okay, this last one might have been the most challenging because we start with a neutral and it's probably not something you've seen very often. But we are going to add a proton to this. So we're going to end up with CH3. We could write it like this, NH3 plus, that's totally fine. You could do CH3, NH2 plus. Either one of those is acceptable. I mean, just recognizing that you add a proton is what we want, okay? And we are increasing that charge. So again, +1. So we go from a neutral, we have to add a proton, we do +1, okay? And then OH minus. That make sense? Cool. All right, yes? So for the PO4, SO4. Oh. So this, is that what you're asking? That's actually not correct because it adds 2 protons. So only add 1. Yeah. For these, they're only what I've done so far. Yeah. And I'll post that eventually today. Well, for these, I just like to use the full water. There's a question what we've got calculating pH, POH, OH minus from an H plus concentration. What's that? Acid-base conjugate pairs.